Dare I say, it's like the Avengers of theorems maybe. And whenever I used to apply it, it felt like creativity was not in the room with us anymore. I do think it's a tiny bit overrated. Like, did any of you actually use it in a math problem? Ever? Like, did you actually use it in real life at any point? Alright, maths fans and fellow geeks, have you ever wondered which theorems deserve the crown and which ones should just stay in the backseat? Well, maybe not, because this is indeed extremely unnecessary, but that's why I'm here with you today, to provide your daily dose of pretty cringy math puns and to bring you offense when I will be roasting your favorite theorem, of course, playfully. And let's not forget about putting my Oxford Maths degree to good use. Okay, so today we will be ranking some of the most famous math theorems based on their utility, their elegance, and of course how much they make the average student suffer in an average math class. Okay, so let's see the tiers. So we have from the very top, which is the very best, to the lowest, proof positive, which is for those theorems that are absolutely essentials, they're game changers, or the most elegant. Then right below we've got solid foundations, which is for those theorems that are still pretty crucial but not as iconic as the top tier ones. Then we have the pretty neat tier, which is quite self-explanatory. It's for those theorems that are interesting, they're still useful, but they're not quite top league. Then we've got our workhorse wonders, which are for ones that are functional and reliable, but not really mind-blowing. Then, a little math pun here and there doesn't hurt anyone. So as the name suggests, theorems that are less exciting or only relevant in niche scenarios. And at the very bottom, we've got forgotten theorems, the ones that are very rarely used or just plain obscure. And we'll see which ones fall in each of these tiers. So starting off really strong with Euler's identity. Come on, this isn't just a theorem, it's a mathematical masterpiece for real. E to the I pi plus 1 equals 0 ties together 5 of the most important numbers in the whole of maths, really. And it's just one elegant equation. Dare I say, it's like the Avengers of theorems maybe? All of the big ones, all of the big names united for a single cause. It gives the same vibes, doesn't it? If I'm going even further, if this theorem were a piece of art, it'd be the Mona Lisa. And just like her smile, it's beautifully enigmatic, isn't it? So yeah, it gets a proof positive for me without any further ado. So okay, another classic, we've got the quadratic formula. Ax squared plus bx plus c equals 0 has this trusty formula to fall back on. It's not glamorous, but I do remember watching my teacher do the proof in class when I was like 12 years old, and at the time I thought that it was pure genius. I'm sorry, I did not know any better, so what can I say? Yeah, it's reliable, always gets the job done, really, It's like that one friend who always has a solution, even if it's not the most creative one, but it can always come up with something. I feel like this is how I would describe the quadratic formula. So yeah, it's pretty mid, but pretty neat. Yeah, we'll leave it in pretty neat, I think. Okay, we have the central limit theorem. This is the unsung hero of statistics, isn't it? It tells us that under certain conditions, the average of a large number of random variables will be normally distributed. In other words, it's the reason we can pretty much always use bell curves to predict everything from test scores to stock prices. It's not very flashy, and it's just an approximation after all, but it is very reliable and makes you see the whole picture really quite instantly. So yeah, I think solid foundations will be reasonable for it, to be honest. Alright, the binomial theorem. I'm not gonna lie, I am not the biggest fan of it. I know it's very important, but still. Yeah, so the binomial theorem gives us the power to expand binomials raised to any power, saving us from theoretically pretty tedious multiplication. I remember I was preparing for Olympiads, right? And I was desperately in need of a tool to do this kind of thing. And I was very disappointed that the binomial theorem was it. So it makes your life a tiny bit easier, but it's not really saying much. Like, it doesn't get a lot of love, you know what I mean? I think it's like elevator music or like background music, It's not mind-blowing. So yeah, kind of meh. Cauchy's integral formula. Now this is actually a pretty nice one. It's pretty niche, but in complex analysis, this formula is like magic, trust me. And it gives you the value of a function within a contour if you know its value around the contour. So it's not everyday math, but in its domain, it's very powerful and elegant. So yeah, pretty neat I would say. Okay, L'Hôpital's rule. I'm quite a big fan of this, quite a big fan to be honest. It feels like the loophole in calculus, you know? Basically lets us solve indeterminate forms like 0 over 0 or infinity over infinity. It's not the fanciest theorem out there, I will give you that. And I remember when I first learned calculus, I was feeling very rebellious in a way, and I just applied it without even checking if we had an indeterminate form, which is not ideal. It is very practical though, if you know when to use it. And it's like finding an alternate route, you know, when the main road is blocked. So yeah, like it's like a workhorse wonder. I think that's pretty reasonable for it. Yeah, we have the weak and strong law of large numbers. The laws of large numbers are all about how the average of random variables converges to the expected value as the sample size increases as it goes to infinity. It's pretty intuitive, and for sure it's very important in probability, but they both tend to be overshadowed by their, let's say, flashiest relatives, such as the central limit theorem, for example. And I remember being very upset when I expected the proof of the strong law to be as nice and easy as the proof for the weak one, and then having to deal instead with backwards martingales, which is not really the nicest memory I have. So yeah, forgotten theorems, it gets overshadowed quite a bit. Alright, we've got the Chinese remainder theorem. Yeah, so that's quite the staple in number theory, I suppose. It helps us solve systems of simultaneous congruencies. It's pretty decent, pretty clever. It's got some nice applications in CS as well, so in computer science, but it's not necessarily a crowd pleaser. It's a bit tedious, as I've said, and whenever I used to apply it, it felt like creativity was not in the room with us anymore. So yeah, let's just give it a meh, I suppose. Okay, we've got basis theorem now. Now this is actually a good one. So these theorems bring together the power of probability into the realm of decision making. It's very much used in practice, it's very useful in everyday situations, and it's like everyone understands what it says really. So it's basically by updating probabilities based on new evidence. It's a theorem that lets us refine our initial predictions and just make smarter choices overall. So it's basically the theorem that says, hey, let's think about that logically. So yeah, it does deserve a proof positive in my opinion. I feel it's fair. Alright, Green's theorem. This is applied maths at its finest, I would say. It makes our life easier by turning complex line integrals into double integrals. So it gives us a very neat trick, I would say, and it's a staple in fields such as fluid mechanics or electromagnetism. I guess we shall put it in pretty neat. Yeah, that's pretty reasonable. After all, it's got the older sibling, which is Stokes right here, which I think deserves a higher tier, a solid foundation, simply because it generalizes both Green's and Gauss's theorems, and actually many more. It turns a surface integral into a line integral and also vice versa. So it's definitely indispensable for both physicists and engineers. It does provide a bit of a headache from time to time when you have to deal with it, especially for the average student. But you know, you can't argue with the facts, solid foundations. Euler's line. I absolutely love geometry, I'm not gonna lie. I will try not to be biased whenever a geometry trick appears, but I cannot make any promises here. So like, come on, Euler's line must be like the cool kid of geometry. It's a straight line that goes through some of the most important points in a triangle, like the centroid, the orthocenter, the circumcenter, and also the center of the 9-point circle, which is really cool. It's geometrically elegant, it's very satisfying, and yeah, I don't care if I'm biased, it's proof positive for me. Alright, Fubini's theorem. It is all about efficiency. Yeah, I would say it's all about efficiency. It lets us swap the order of integration in double integrals. It's a workhorse for anyone dealing with multivariable calculus especially. It makes integration a little bit less of a pain than it normally is. But you cannot lie to me and say that you have not been guilty of swapping the order regardless, without even checking if Fubini applies. So yeah, it's quite meh to be honest. Cantor's diagonal argument. I cannot really say much about this. It just feels like the ultimate mind-blown moment in set theory as a whole, I think. So by showing that the real numbers are uncountable, it just opens the door to very bizarre and beautiful worlds of infinity. So yeah, it's pretty neat, that's all I can say really. We have the holy grail of maths in front of us, ladies and gentlemen. This is like the mystery novel of number theory, isn't it? Nobody solved it, but everyone has their opinion. But I do put my money on James Maynard solving it. So yeah, mark my words. I do think that James Maynard will actually solve it. So proving or disproving it could actually redefine the field. It would be the ultimate what if. I would put it in proof positive simply because it would make so many things true. It would unveil so many mysteries. But come on, it's not really a theorem because it's not proven. It doesn't have a proof, so I cannot really put it in any of the tiers. It would just not be fair for the other ones that actually have a proof. So I would put it in forgotten theorems just because it hasn't been proved yet. And then in a few years, if it's eventually solved, we will open up this discussion again. Alright, we have the law of total probability. This theorem is just about making sure that you account for all possibilities when you calculate probabilities in general. So it's the leave no stone unturned, I would say, approach to the word of probability. It's very essential in theory. It often is taken for granted in practice, but it's pretty solid. Yeah, it's a workhorse wonder. It's a workhorse wonder simply because it's very intuitive. Okay, we have the IVT. Yeah, the intermediate value theorem. It's a very reassuring theorem. It just says that if a nice function is simply moving from one point to the other, it would cross every single point in between. It's very reliable, right? Like, it just says, oh, don't worry about it, we'll get there eventually. Which I think is quite neat. Yeah, pretty neat. Nothing else really. We have the MVT now. I guess we can do all of the analysis in one go, I guess. So if the IVT was, we'll get there eventually, the MVT is, I told you so. I think that's quite reasonable. So it proves that somewhere between 2 points there is a tangent line parallel to the second line passing between the 2 points. It's all about making averages behave, and while it's pretty neat, it's not exactly lighting up the room by itself. It is though used a lot in very foundational proofs in optimization, which is essential for ML these days. So I think that just moves it up to pretty neat. The chain rule. The chain rule is that one calculus trick that allows you to differentiate any composite function. So it's always handy when things get very tricky. It's very satisfying to apply. You know, in differentiation war cooking, the chain rule would be your trusty kitchen knife maybe. So it's essential, it's quite indispensable. Yeah, solid foundations. Gödel's incompleteness theorem. We're getting a bit philosophical, guys. Yeah, so this theorem basically shook the foundations of mathematics by proving that there are some truths in math that cannot be proven, simply. It's very deep, very philosophical, as I've said. It's like dropping a plot twist at the end of a movie and just leaving you completely questioning your entire existence. So yeah, it's quite mind-blowing stuff, but who am I to put it anywhere else but in proof positive? Okay, Pythagoras. That's the OG that introduced so many of us to the world of geometry, maybe even the world of maths in general. A squared plus b squared equals c squared. It's just a formula we all either fell in love with or were tormented by when we first learned maths in school. I do think it's a tiny bit overrated. Like, don't judge me, it's not even that useful when you get deep enough into math. And it's not even that satisfying, so we'll just say workhorse wonder. I feel it's pretty reasonable. Okay, the semicircle law. Now that's some very particular stuff that we have here. The semicircle law deals with distributions of eigenvalues of random matrices, and it is very niche, even for math enthusiasts. It's that kind of theorem that you appreciate when you're very deep into the subjects, but it's not making any headlines either. I would say that the whole idea of universality in eigenvalue statistics is pretty neat, but it's not like it's gonna change the world, at least anytime soon. But who knows, maybe in the future. Like, don't quote me on that. I'm definitely not an expert. But yeah, for now we will leave it in math and then yeah. Alright, we've got the residue theorem. Now in complex analysis, this theorem helps you evaluate complex integrals by relating them to the sum of residues of the given functions of the integrand. It makes me think of a secret shortcut in a video game, you know, the kind of thing that not everyone knows about, but those that do can just speedrun for the whole game, for the whole tough problem that you have at hand. I say it's pretty neat, but it will get lowered to workhorse wonder simply because calculating the residue of a function will give you a headache, 100%. Like, it's not neat, it's very tedious. So yeah. Okay, we have the law of cosines. That's like Pythagoras' older but wiser cousin, because it can be applied in any triangle. It just steps in whenever you're dealing with triangles that aren't that tidy, that aren't that neat. It's not as universally loved, it's not that useful in everyday life, but I would say it's pretty neat. Like, I solved some problems with it that were quite satisfying, so yeah, pretty neat. Then we've got the law of sines, which is, again, it's great for any triangle, very satisfying when you realize that, oh, this is the tool that I need to use for this problem. It simply relates the angles and the sides in a triangle in a very, very simple ratio. It's versatile, even if it doesn't get as much attention as Pythagoras, but I still think it's pretty neat. Yeah. Alright, Fermat's little theorem. There's a sibling living in the shadow of the very famous older brother. You know what I mean? Yeah, you do. I'm sure you do. So while it's very useful in number theory, it's a very useful tool, especially in cryptography, I think it lacks the wow factor that Fermat's last theorem has, for example. It's pretty meh if you ask me, just because it only deals with primes as well, like, it doesn't break any records, you know. We've got the fundamental theorem of calculus now. Can't say right off the bat this should just go into solid foundations, really. Like, if you think about it, where would we be without the fundamental theorem of calculus? Like, just let it sink for a bit. It's the backbone of calculus when you think about it. It just bridges the gap between differentiation and integration. And without this, calculus would just be like a sandwich without the bread. You know, it would be quite messy, not quite as satisfying. It doesn't get top tier though, simply because it feels a bit too intuitive and you might be just tempted to assume it, to take it for granted without really checking. So yeah, solid foundations nonetheless. The spectral theorem. Now, in the world of linear algebra, this is pretty much a hero. Gives us the eigenvalues, eigenvectors of normal matrices. It's foundational, sure, but it's not everyone's cup of tea. It's more like the steady, reliable background character in a movie, but it doesn't really come nearly close to the main character. So yeah, a workhorse wonder I think is quite suitable for it. Ooh, we've got the angle bisector theorem. Now this is very solid in triangle geometry. It's one of my favorites actually. It relates the ratios of the sides of a triangle to the segments created by the angle bisector. Yeah, it gets the job done, not much fanfare about it. It's pretty neat. I would maybe put it higher, but I know I'm biased in that one, so pretty neat. Okay, we have Thales' theorem. Now for real, this is one of the oldest results in the whole of geometry. It states that any angle inscribed in a semicircle is a right angle. It's pretty classic, pretty essential, gets overshadowed by flashier theorems in modern times as expected. But also, fun fact, in Romania, we call something else Thales' theorem. So I'm not really sure what that's all about, and you can do with that information whatever you want, but yeah, pretty meh overall, I guess. Okay, we have Lagrange's theorem, the one in group theory. So this theorem stating that the order of a subgroup divides the order of the group is essential in abstract algebra. You'll need to deal with it if you study any introductory course in group theory, essentially. Very fundamental, doesn't often get the same attention as other theorems. It is very useful though if you work in the area, and I would say I did use it quite a bit. So yeah, workhorse wonder suits it, I think. Alright, Fermat's last theorem is the last theorem in this tier list as well, so we're just sneaking this one in at the end, aren't we? Yeah, so for centuries, you know the story. This theorem has taunted mathematicians with its apparent simplicity but resistance to proof. Andrew Wiles was the one that finally cracked it in 1994, proving that, you know, x to the n plus y to the n equals z to the n for n greater than 2 does not have any integer solutions, which is mind-blowing in itself. It's so simple. It's like the Moby Dick of math, you know? It's elusive, but also satisfying to be finally pinned down, I would say. Do I really believe that Fermat had that marvelous proof that he just could not fit in the margins of his notebook? not really. That just doesn't sound plausible at all, especially with the tools that he had available at the time, and thinking about how long Wallace's proof was and the fact that it literally used so advanced maths. But it's not like we'll ever know that for sure. So yeah, one can speculate, what can I say. It's nice looking, it's very interesting how something that looks so innocent can just have such a complex proof. But did any of you actually use it in a math problem? Ever? Like, did you actually use it in real life at any point? Honestly, it is pretty meh for that reason, like, let's be honest. But we do need to give it points for its very unexpected nature. When you do think about it, the n=2 case has infinitely many solutions. It gives you those very nice Pythagorean numbers. And then when you bump it just one step higher, you don't get any solutions. They just deserve some extra points by itself, even if we don't consider the proof. So yeah, solid foundations, despite my rant. We give it the solid foundations. Alright, and there we have it, guys. This is our final tier list of very famous math theorems. Do you agree? Do you disagree? Let me know down in the comments below, and also let me know if I missed any of the very important theorems. What else would you include in the top tier, in the very bottom tier? I do think it looks pretty neat. Let me know what you think. Of course, this was all just for fun, and remember that every single theorem has its own place in the tapestry of mathematics. So there are no hard feelings at all. Even if I put your favorite theorem in the bottom tier, please don't take any offense. I do personally believe that every theorem has its own beauty in it, and it can be applied in very, very satisfying situations, despite what I've said about them just now. So yeah, if you enjoyed this video, please make sure to give it a thumbs up. Subscribe to my channel if you want to see more funny or more serious math content and also university content. Follow me on Instagram for more content if you feel like it. I definitely am a lot more active on there. And don't forget to hit the bell to get any notifications whenever I post, to be the first one that actually watches my videos. And yeah, thank you so much for watching, and I do hope that I will see you in the next one.
I'm sick of daydreaming, I just want the feeling of you in my bed. I'm down to just waste time right below your waistline. Want you by my head.